All right, let's get underway with our first topics. So in this subject, we look at Earth system processes, and they've been going on for a very long period of time. And so in this subject, I like to go way back into time, and right back to the beginning of time, in fact, and begin with what we know as the Big Bang. Now, nobody knows exactly how it all started, or even when it started, but we think around about 16 billion years ago, something happened to create the universe that we now look at when we look up at the night sky, and in fact that we exist in, of course. So before that time, there was nothing. People say, well, what happened before the Big Bang? Well, the answer to that is, in fact, nothing happened. Time itself, the way we perceive it, in fact, time is only a human construct, began also at the time of the Big Bang. There was, in fact, nothing before the Big Bang, as far as we know. So at that time of the Big Bang, all matter was created in this enormous explosion, this huge explosion that produced everything that we see around us, and this massive fireball of matter and energy. And somehow we went from this huge explosion to an extremely ordered universe that we see today, exemplified by the order, generally sort of environmentally speaking, that we see in the planet Earth that we live on. So how did we get from this huge explosion to this lovely Earth? Well, let's have a look at what the Earth is made up of. And these are chemical formula for some common elements and some common compounds, many of which you'll recognise. H2O, of course, is water, C is carbon, Fe is iron, O is oxygen. And they exist all around us. So we've gone from this massive explosion of energy and matter to a very ordered universe, a very ordered Earth, where we have these compounds and elements that exist all around us. So let's have a look at that in a bit more detail. Each of the elements are made up of what's known as an atom. Now, you've heard of atoms. And this is a sort of a stylized diagram or a simplified diagram of what an atom is. So an atom consists of a nucleus, and in the nucleus are neutrons and protons. And then whizzing around the nucleus are electrons. Now, the number of neutrons and protons in the nucleus is actually important. Now, if you did any study at school, any chemistry at school, maybe you did some study at school. If you did any chemistry at school, you probably came across, or you should have come across, this diagram here, which is the periodic table of elements. Now, if you didn't do chemistry at school, don't panic. We're just going to look at this very simply. And what we can see is a whole bunch of different colours and letters all in these squares. Now, what this table is showing us is all of the known elements in the universe, all the ones that have been found. And in the table, you'll see each of the squares has a letter. So in the top left-hand corner, the letters H stands for hydrogen. Going across to the right-hand side on that top row, He is helium. Second row, lithium, beryllium, then boron, carbon, nitrogen, oxygen, fluorine, neon, and so on and so forth. Also within each of those boxes is a number. Hydrogen, the number is 1, helium, number 2, lithium's 3, and so on and so forth. That's called the Z number, also known as the atomic number, which is also the number of protons in the nucleus. And that's what gives each element its different characteristics. So exploring that a little bit further, here we have, let's get rid of the electrons whizzing around the outside and just have a look at the nucleus. Now, if the protons were the blue balls in this simplified diagram, how many are there? Well, let's count them. Let's see. There's 1, 2, 3, 4, 5, 6. So how many? So that's how many protons there are. So what's its Z number? Its Z number is 6. And if we look at our periodic table of elements, you can see there that the element with the atomic number of 6 is in fact carbon. So that element is carbon. Carbon is the only element with 6 protons in its nucleus. Now, one of the key things to understand about chemistry, and certainly at the atomic level, is that atoms can combine. Now, they can combine in these extraordinarily large facilities. This one is on the border of Switzerland and France. And it's a facility that whizzes around atoms in different directions around that big circle highlighted by that yellow line there, and drives them into each other to try and get them to combine. And that process where atoms combine is known as nuclear fusion. You've probably heard of that. The problem is it needs extreme temperatures. So although these facilities exist around the world, they are extremely expensive to run. And the process of getting atoms to combine in nuclear fusion, although it results in a massive amount of energy being produced, proportionate to the amount of matter in the atoms that was forced to combine, the ones on Earth, the facilities on Earth, require currently more energy to force those atoms together than is produced by the nuclear fusion. So they're used for experiments and high-end chemistry and physics. They're called particle accelerators, but there is a place where this happens all the time and it doesn't require huge amounts of energy input into the system. It occurs naturally, and that's in suns and stars. What happens when you get nuclear fusion occurring is you get energy produced. So every day when we see the sunlight from the sun and feel the heat when we're standing outside, that's the energy produced as a result of nuclear fusion. So let's have a look at it in a bit more detail. All right. So let's start with 2 elements of Z number of 6. Correct. Carbon. So we've got 2 elements of carbon, and let's say we force them together in a particle accelerator on Earth. We end up with a nucleus with how many protons in it? Because we've literally forced them together. So we've now got a nucleus that is twice the size. 2 elements of carbon coming together gives us a nucleus with 12 protons in it. The Z number is 12. And what element is that? Well, if we look at our periodic table of elements, you can see there is magnesium. All right, good. So that's basics of nuclear fusion. We get a new element and we get some energy. Let's go back to the start of the universe, that Big Bang that we looked at before. And let's come forward in time. Less than a minute after the Big Bang, the temperature of the universe was about 1,000,000,000 degrees centigrade, 1,000,000,000 degrees Kelvin, but at that scale it's about the same. So extraordinarily hot. The universe existed of neutrons, protons, electrons, and some other particles that were whizzing around the universe, but we'll just concentrate on protons, neutrons, and electrons. These are all whizzing around in this extremely hot, high-energy universe. And all of those bits of matter, the neutrons, protons, electrons, they weigh something, they are matter. We're whizzing around away from each other. Now, we come forward a little bit to 3 to 4 minutes after the Big Bang, And like anything that's hot, if you leave it, it starts to cool down. And so 3 to 4 minutes after the Big Bang, the energy of the universe and the temperature decreases slightly. So it's not 1,000,000 degrees centigrade, it's now only 1,000 million degrees centigrade. And because it's cooled down slightly, some of those protons can start to come together. We, of course, had hydrogen, 2 protons coming together. We had helium, and there was also the ability for 3 protons to come together, and we'd get lithium. Now, this is all due to the fact that these early protons, neutrons, and electrons all had mass. They actually weighed something. And so anything with mass has a gravitational attraction. You have a gravitational attraction, I have a gravitational attraction to everything else that's around us. The reason we don't sort of bang into each other when we're walking down the street is because we have this very large thing called the Earth underneath us, which has a much larger gravitational force, overriding our own forces of gravitation. But it's nonetheless measurable. Everything that has matter has a gravitational force, and it can be measured. It's just that we're not sensitive enough to experience it. So 3 to 4 minutes after, we had mostly hydrogen still, but there was some helium and some lithium nucleuses forming. Now, 380,000 years after the Big Bang, those electrons started to join up with those nucleuses, and they tried to balance out. In this case, it's an electrostatic charge. The negative charge of the electron was attracted to the positive charge of the proton. So that then started, and that then produced our first actual atoms. Now, so that existed for several 100 million years. It's still mostly hydrogen. It's still pretty hot, relatively speaking, and it's starting to cool down. It got to the point about 300 million years later where it was cool enough for those atoms of hydrogen to start to come together via the force of gravity and start to coalesce in these huge clouds. We call them nebula. Now, this is a present-day nebula called the Eagle Nebula, but nonetheless, it's a good representation of what was happening in that early universe 300 million years after the Big Bang. So you start to get this differentiation in the universe. At the start, everything was just spread all through the universe, and then after a few 100 million years, things started to concentrate in certain parts of the universe. Again, all due to the fact that things like to come together under the force of gravity. What it also meant was that because of the physics of the way the universe was set up, things started to come together, and then they also started to rotate. And we see that rotation in everything in the universe. All right, so that's 300 million years after the Big Bang. We've got gravity attracting these particles of hydrogen gas. Now, as they get closer and closer under the force of gravity over millions of years, they get closer and closer and closer, get more and more and more and more coming together. When you get so much of it occurring that they start to really bump into each other. And it's a process of things bumping into each other. Now, just like me rubbing my hands together, what am I producing? I'm producing a sound. Well, that probably wasn't happening. Nobody can hear you in space. But it's also producing something else. You rub it long enough, what are you doing? Well, you're warming up your hands via the process of friction. Well, that was exactly what was happening also in these massive gas clouds. 300 million years after the Big Bang, friction was occurring, but on a massive scale, producing tiny amounts of heat with each collision of those gas particles. But nonetheless, this produces heat in these gas clouds. And that heat continued to grow and grow and grow and grow and grow and grow until you have a star forming, because what you have is you have nuclear fusion occurring. So there's so much heat that now in these clouds that the particles are starting to then be forced towards one another. So they're causing friction, but that heat that's generated is also forcing them apart into one another. And when that starts, it produces more energy, which produces a chain reaction, which produces this process of nuclear fusion. And that's how we get stars forming. So in our sun, as in all stars, what's happening in the core is this process of nuclear fusion. That's generating the energy that we are experiencing. Let's have a look at that in a bit more detail. So what's happening inside our sun and other stars? We've got one proton of hydrogen being fused together with another proton of hydrogen, producing helium plus energy. And that continues on for billions of years. And then eventually, when all the hydrogen in the core is consumed, helium starts fusing because there's no more hydrogen left. Simplifying it, but nonetheless, it's appropriate. When the hydrogen's gone, the helium starts to fuse. And you get, let's say, 3 heliums come together, each with 2 protons. What do you get if you fuse together 3 protons of helium? Well, you get a new atom that has 6 protons in it. And what's that? Well, we saw that before. That's carbon. So carbon is forming in the core of suns. Then, if the sun is large enough, the star is large enough, then carbon can start fusing with some of the helium. And what does that produce? Well, now we've got an atom with 8 protons in the nucleus. We look at our periodic table of elements. There you go. It's oxygen. Let's say we take the carbon that's produced by those heliums, a couple of oxygens and 2 more heliums, and we add all those protons up. We get a number, periodic table of elements. Let's see, that's 6, 8, 8, 2, and 2. That's right, so that's 32. There they are. And what's that in the periodic table of elements? It's iron. And so what happens then, usually, now some stars, they don't do anything else if they're small enough, so they just sort of continue and just burn as a white dwarf. But other suns and stars, if they're large enough, they will continue to fuse with the iron starts to fuse with other elements, and they get larger and larger and larger and larger and larger until eventually the core of that sun becomes so heavy and so dense with all of these new elements being formed inside the core of that sun, these heavy elements, that eventually, at about the point where iron's being produced, it gets so heavy and dense that the sun collapses in upon itself, creates a huge amount of energy that creates fusion of even the much bigger elements occurring. And at that point, we call that a supernova, because that collapse produces that huge amount of energy, and then the sun, that star, explodes and throws out into the universe all of the elements that were in that star at that point. So not only the leftover hydrogen, if there is any in the outer parts of the star, but then the helium, the carbon, and the oxygen, and the iron, but the heavier elements like uranium, aluminium, sulfur, silicon, they're all thrown out into the universe. Now, the only place that you can get these elements forming is in stars. The only place. It doesn't form on Earth. It doesn't form in some lab somewhere. The only place you can get these elements being created is in the cores of stars. The only place. And it's occurring now out in the universe, and certainly occurred in the past. And if you think about it, what's our Earth made up of? We saw before. Well, we've got water, and there's carbon in the trees, and there's iron in the rocks, and there's water in us, and there's carbon in our skin and bones, and there's iron in our blood. It's the only place that these elements can be created is in the cores of stars. What does that mean? It must mean that we too are made up of stardust. So, I like to start this subject with that with that lecture. It's kind of entertaining, I hope. Makes some people think, some people know it. Although I tend to find that most people, it's new to them or they haven't thought about it. Yeah, and you can take what you want from that one. All right, so that ends our first little lecture, and stick around, hopefully. Okay, so that ends our first lecture. Hope you got something out of it.